Okay, our next topic is assessing risks of disease, all right? So you remember what I said about epidemiology? You have the burden of the problem, and then you want to also understand not just the size of the problem, but the underlying risks that contribute to that problem, and also the effect of interventions that can reduce the problem. Today we're going to be talking about risks, about things that can make things worse, all right? So you already have the burden of the problem, which is inherent to us biologically. If we just live and do nothing apart from drink and eat and sit around, we will still all start getting diseases. This is our like inherent burden of disease that we'll all have with age. But on the top of that, you can do things that make you more prone to disease, and that are going to increase the burden of disease in the population. So let us think through how, in epidemiology, can we figure out which exposures or behaviors or things that we can do are actually increasing the risks of disease and sometimes even causing a disease from out of nothing. This graph is quite useful because it starts with an ultimate risk, which is the risk of death, okay? So the risk of death is almost like a sum total of all the lifetime risks. And so they all add up to eventually a risk of death. And look, if you are, this is for the UK, if you're less than 1 year old, your risk of death, and this is a logarithmic scale, your risk of death is 1 in 200, 300, something like this, all right? So it's not negligible. It's difficult to survive the first year, obviously, but then it really drops very quickly, and this is the stage where your risk of death really drops to a minimum. From 5 to 14, you're least likely to die. It's 1 in 10,000. And after that, it just starts going up again. You're becoming more and more likely to die. So when you get to 84 plus, your risk of death becomes like 1 in 7 every year, all right? So each year you have 1 in 7 chance to die, or actually next year you have 1 in 6 and maybe 1 in 5, so you get more and more likely to die. And you can see that for men and women there is a difference. Men always have a bit higher risk of death than women, even from the very start of life. But look at this difference here from 15 to 24, when men start doing all sorts of crazy things and drive cars and get engaged in all sorts of ridiculous activities. So this was their fighting years, when their hunting years, historically, obviously, when they were hunters and gatherers. I would obviously be a gatherer. I wouldn't last long as a hunter, I think. But this is when men obviously are high on testosterone, and they do things that put them under higher risk of death than women, all right? Now, there is another risk which is completely disproportionate to the risk of death, and that is the risk of marriage, okay? So, when you're least likely to die, you're most likely to start thinking about getting married. Obviously, you're most optimistic about life. And marriage, we can see here, was introduced very, very long time ago. So maybe a couple of thousand years, maybe even more. And when you think about it very carefully, in those days, the life expectancy was what, 30 years maximum, maybe 32, 3, maybe 27. So people didn't live long in those days. So marriage must have seemed as a very good idea to get two people together when they're 15, and then they basically would get children, and this was making them stay together and take care of their children, and then they would 15 years later simply die and let their children, who are now 15, get married and procreate further. So that kind of worked, that concept of marriage, right? But what happened in the meanwhile is that the life expectancy has, this is what life expectancy or risk of death was when the marriage was introduced. But look at what happened in the meanwhile. Now life expectancy extended so much beyond those 25, 30 years when marriage was introduced, that now you have people living in Japan for 115 years, 120 years. So there are some people who have been married for 100 years, and I can tell you safely from my own experience that after you're about 40, you can't even stand yourself anymore, let alone someone else. So you have to be very, very careful who you are picking as a partner these days and getting married to, because you may be in that marriage for much, much longer than you think, especially with all these phenomenal advances of science and technology which are extending the lifespan. If there is some unbelievable extension of lifespan during your lifetimes, which is completely possible with all the strange stuff that is now going on in science, you may end up with someone for 1,000 years or so, and that's a prospect that you should really start thinking about. So be careful who you're choosing, because you may be in it for a very long haul. All right, so now looking at the life expectancy as another summary measure of these risks, and relating it in some way by income, you can conclude one very important thing. And if this is the only thing that you remember from this whole course, I'll already feel good that I taught you something. Look at this x-axis. This is money on a, I think, logarithmic scale or something like this, and this is the linear scale of health. So this is life expectancy at birth. How long are you expected to live if you were born in some of these countries? And this is the wealth of those countries per capita that they generate. So you can see that there is a relationship, very clear relationship. The wealthier the countries, the more wealth they generate, the longer people live. So obviously, what is the greatest health risk of them all? Clearly, the greatest health risk of them all is to be poor. And that is the sad truth about the world today. You know, the poor people not only are poor, but they also, unfortunately, have much poorer health as a consequence of everything related to poverty. And there are complex relationship between poverty and health, obviously, but there is a very striking relation, obviously, here. But that's not the whole story. So remember, you know, if you want to be healthy, it's good to be wealthy. And if you want, if you don't, I mean, if you know what it wants, hopefully, to be terribly poor or unhealthy, but those two things also seem to be related. Okay, now that we established that the richer you are, the longer you live, which means probably the healthier you are as well throughout most of your life, there's just one part of the story. But look at this. Let's look at Kosovo and Vietnam here, and look at Cameroon and Nigeria here. All right? What do we see? We see that there are some countries which only make like $3,000 per capita, only produce that much wealth a year. And there are some countries with the same level of wealth which can expect to, for all their population, so this is an average life expectancy, to live to be 75, Kosovo and Vietnam, whereas Cameroon and Nigeria, with the same level of money, they live to be 47. This is a massive difference, 47 and 75, and they're equally wealthy. So it's not only about wealth, clearly, there must be other stuff. Because how is it possible? If it's just wealth, then you're wealthy, so you're healthy. But clearly, these people are no wealthier than these people. And look at the difference in life expectancy. It's like 47 or in Nigeria and 75. That's almost 30 years difference for all the people living there. And in Nigeria, you have 100 million plus people. In Vietnam, you also have about 100 million plus people, and this is their average of 100 million people differs 30 years. That is unbelievable, almost, right? So it's not only about wealth, it is obviously about how this wealth is distributed in the population. If it's very equally distributed, like in Vietnam and Kosovo, then everyone gets a chance to benefit from this wealth, and look how much you can achieve. You can get them to have life expectancy comparable to Poland or even Qatar here, which is phenomenally more wealthy than they are. Whereas in Nigeria, with the same wealth, but this wealth doesn't trickle down to the whole population. The wealth is obviously kept within certain parts of the society which keep it for themselves, and it doesn't trickle down to the rest of the society, and this is why you have phenomenal base of this population which is poor and which is just as poor, as you know, unlikely to live long as if they were in DR Congo or Burundi or Zimbabwe, or very, very poor countries, much poorer than Nigeria. And you can see actually one other thing, which is how quickly you can up your life expectancy with not that much money. So, you know, the difference from having $2,500 and $25,000 is only a few years. So 10 times more money, but only a few years more in life expectancy when you look at this, right? So, but look at the difference between you know, having $500 and $2,500. Okay, I have to be fair here and say that this is not all due to poverty in sub-Saharan Africa, and you can see that the dark blue colors are all sub-Saharan Africa. This is the effect of HIV/AIDS, because this year is, I think, 2000 here. Oh no, 2010. But still, HIV/AIDS, huge effect. Look at the effect, and look how we have all failed Africa and left it behind all these countries that are racing forward and getting wealthier and healthier. So clearly a tragedy, really, and unacceptable. Similar example. Look at some African countries that managed to get wealthy. South Africa, Botswana, Equatorial Guinea, Gabon. Look, they are making $10,000 plus per capita, and because of massive inequity in these populations. Look at South Africa, for goodness sake. I mean, this is really 52 years life expectancy. Okay, HIV, there was a massive problem as well, and particularly a funny political situation where they had a Minister of Health who didn't want to acknowledge that HIV was a real problem. So, but Botswana and Equatorial Guinea, for goodness sake, 55 years for Botswana with $15,000, and look at Costa Rica and Cuba. Cuba is a great example, less than $10,000, and they have a life expectancy equal to the United States of America, which invests many times more in their health system than Cuba do. In fact, when you look at America here, they should be here. So Americans also must have a lot of inequity in their population, because when you look at the wealth that America has, which is massive, they should really be living 85 plus. They should be ahead of Japan and Germany and Italy and UK and Iceland and Sweden and South Korea. But they're not. They're actually not doing that well at all. So their health system is the most expensive yet very inefficient health system. They believe they believe so much in capitalist liberal ways that they thought that the health system should also behave according to those ways, and they made it very liberal. But the trouble is that it seems that this is one area which really isn't well suited to that kind of thinking, because countries such as Japan and Hong Kong and Singapore and in France, they have so much better and more efficient health systems. They deliver so much return in terms of health on investment. So clearly health economics is a completely separate field of economics which does not seem to comply with all other rules of economics, okay? So remember this, health economics is not as simple like let's just do liberal capitalism and it's all going to work itself out, as it usually actually does in other walks of life, in trade and so on, but not in health. In health, obviously, it is good for the country to do some planning and intervene. Otherwise, costs can just spiral out of control very quickly. So what are the risks of the poor people that make them so less likely to live longer? Well, obviously poverty, obviously lack of food, water which is not drinkable and not safe, very poor health systems, very poor sanitation, as you can see here, and then all sorts of other things, lack of money that the governments can invest even in vaccinating their children, so they're getting the diseases that they should not be getting. Look at the health systems and hospitals and state of infrastructure there. Look at the living conditions for many people in the world. Look at guns and violence and war that is usually prevalent in poor societies. This is how kids play in some African countries, and then you have landmines left, and then you have, on the top of all this poverty, you have all these other problems, landmine victims and so on and so on. So So clearly poverty is associated with a lot of other things that are going to make health of the population worse. But wealthy people, surprisingly, also have their own specific risks which poor people don't. For example, alcoholism is a thing of, okay, it does exist in poor societies, surely, but it's a big problem in wealthy societies too. Smoking started off in wealthy countries, now it's spread to poor countries, unfortunately. And then obesity is a massive problem because it's really funny how, you know, humans really only need three things. They need food, water, and air. And we must have been selected for these things because in the time of scarcity of oxygen, only those who can withstand lack of oxygen would survive. If there was scarcity of water, only those who can withstand some scarcity of water would survive. And if there was scarcity of food, only those who would be able to survive lack of food would survive and breed the new generation. So if there are so-called selective pressures on us in those three main things that we need for life, then there would be a signature, and the signature would be that we can withstand the lack of it for a long time. So let's think about breathing and oxygen. How long can we survive without oxygen? Very, very short time, maybe, you know, a couple of minutes, and that's it, then we die. So clearly there was no selection for this historically. There was always enough oxygen for everyone. Water, we can live without water for about a week maybe, all right? So clearly the fact that we can withstand without water for longer than a day or two or five means that there must have been shortages of water historically, and only those who managed to withstand it gave rise to new generations. So we were selected for being thirsty. But without food, we can last for as many as maybe 40 days. So we can go on without any food at all, as long as we have water, for more than 3 weeks, maybe even 4 weeks, and some people even longer. And then, which means that we were always starving as a species. You know, we probably weren't made to withstand so much starvation, but only those who can handle being without food for such a long time can survive. Because surely there were periods when there was just winter and snow, and parents were sick, and just nobody was there to fend and to fetch any food, and you know, kids and adults just needed to somehow get by. Those who didn't, they died off. Those who managed, they were positively selected. So we are the first generations that are not experiencing massive shortages of food, and what this does to us is that we are all genetically prone to obesity. Now some people are trying to find genes that predispose you to obesity. There may be some, but frankly we are all predisposed to obesity because we're not used to having food all around us all the time. We're for the whole history used to be starving all the time, okay? So one funny thing is that some studies are showing that prison population seems to be least likely to have morbidity of diseases and so on. Why would this be? I mean, some people are still questioning this, but some people are explaining this as a lack of stress. I know that you would not think of prisons as places where there is no stress, because in all American Hollywood movies, prisons are portrayed as these places where there is a lot of all sorts of horrors going on. But frankly, in prisons today, the days are very standardized. Each day is the same, and you have your routine, you get fed, you get exercise, and funnily enough, you know, it seems to be almost more stressful and worse to be living your daily lives and coping with all the stresses of life than to be put in that kind of situation where you don't have to worry about much, and you just go through life and somebody else worries about everything. So that's really strange. It's almost like an analogy to animals in the wild versus animals in the zoo. People were concerned about animals in the zoo, but animals in the zoo tend to live 30–40% longer than animals in the wild. And of course, they're all obese and they're all having diseases of obesity and so on. But frankly, you know, they don't have to worry about their predators and problems and the food every day and make a kill to be able to feed themselves. So it's really funny how it seems that maybe it's good to be cared after and not having to do everything yourself. That may be healthier than actually being out and needing to worry about every single thing. So stress may be quite important. Okay, so what happens within our lifespan? So within our lifespan, which is clearly limited by both our biology and our wealth, we can be more or less healthy or sick. So we can ask ourselves, why are some healthy and others sick? Well, this depends on our own personal risk profile, which will over time inevitably lead to either better health or poorer health. So with some risks, we are simply born. They are genetic. We can't do much about it yet. Having said that, all sorts of progress is happening in genetics, and the method called CRISPR is now allowing us to change our own genes in a living cells. That's unbelievable. So this is not the matter of this talk, but it's good for you to be aware of this. Other risks we acquire as we go through life. So they can be environmental, like nutrition, psychological well-being, substance abuse, exposure to toxic agents, irradiation, physical fitness, behavior, lifestyle, sanitary conditions, and so on and so on. So many risks that we acquire. Only genetic ones we're born with. We have our blueprint in our first cell, which is 3 billion letters. That is like a big library with thousands of books, and they're all in there and telling this first cell to develop into a large organism. This is precisely like you had a brick with information how to build the entire mega city with millions of people and everything in it. That is the same. So if you think this is quite strange, it is strange. It's absolutely miraculous, you know, that we get born as a tiny cell which we can't even see with the naked eye, but there is information in there how to build a whole organism and how to get out of our mother's womb and last out there for 100 years or so in any imaginable circumstance. So that's quite unbelievable, really. You know, it's difficult for us to grasp this. Okay. So that, with those risks, in this information we were born with, we couldn't do anything for a very long time. But now it seems like we can even change that, which is absolutely remarkable. And never mind, we can also affect the environmental risks too. So let's think about how these risks, which I just told you about, work together. Let's say this is Homer Simpson, who's getting his first heart attack, and there are some genetic risks, and you see that you can have 2 alleles at each part of your DNA. Let's say that the blue ones are fine, that's all fine, that's wild type, which we all have. And then let's say that yellow ones are mutated ones, which are strange and causing some damage, all right? So that's a piece of information that's not just right as it should be. Then he could be smoking, he could certainly be visiting McDonald's a lot or some other food chain, and he could be exercising. So these are the risk factors, but this is a protective factor. So depending on what you're doing, you are changing your risk profile. And let's make it extremely simple. Homer Simpson, heart attack, and 3 risk factors and 1 protective factor. Let's see how they all work together. So let us assume that the frequency of this allele in the population is, there are 20% of bad alleles which predispose you to myocardial infarction, and 80% of good alleles which are not predisposing you. So if you have that kind of a frequency of alleles in the population, this is what you'll have if this is 100 people from here to here. If you fit 100 people on the x-axis, 64 of those people will have a genotype big A, which is fine. No additional risk, okay? But 32% of people will have either big A, small a, or small a, big A, This is the orange part of the axis. So 32% of people will have some predisposition. They will have this situation here, yellow and blue. 4% of people will have yellow and yellow, both alleles bad, all right? So what does this translate to in terms of expected age of the first heart attack? For these 64 people, it is going to be 73 years. This is what they're born with, you know, the predisposition of your first heart attack, about around 73 if you have a wild type. Now, what about these 32%? Well, they will get it 10 years sooner, around 63, okay? But look at how bad is it to get 2 bad copies of the predisposing gene. You are going to get it then, if you're so unlucky, somewhere in your early 40s. And we do have people who do get heart attacks in their early 40s, and they don't have any risk factors simply because genetically they have really bad combination of genes. And I'm only talking about one gene here, but actually we have many, many genes contributing to heart attacks and cardiovascular diseases. Okay, so this is what you expect from people based on there's 100 people simply being born and having genes and having an allele which is 20% prevalent in the population, which predisposes people to heart attacks, all right? Now, on the top of that, let's say that people could also be smoking, all right? So if they're smoking, they are lowering the age of onset of their heart attack by 10 years. So no longer will these people get the heart attack at the age of 73, they're going to get it at the age of 63. These people no longer at 63, they're going to get it at the age of 53. And these people no longer at 43, they're going to get it at 33. And actually we do have examples in coronary units of really people in their early 30s even coming with heart attacks. They're usually heavy smokers and obviously having a really bad genetic predisposition. Then let's say that you're eating a lot of high-fat diets. You're lowering the age of onset by further 10 years. So these people, although genetically fine, they could get heart attacks in their 50s because they're heavy smokers and they're eating high-fat diets. These people are really harming themselves because with this one allele, they are actually going to get it in their early 40s now rather than early 60s. And these people are really destroying themselves because genetically having 2 bad alleles, being in this 4% of the population, really unlucky genetically already, but then if they're smoking and eating high-fat diets, they can even get heart attacks in their 20s. That is completely shocking when it happens, but it does happen, unfortunately. And then finally, what can you also do? You can exercise. You can exercise. With exercise, you can actually build up robustness of your cardiovascular system, and you can extend the time you're going to get your first heart attack by 10 years. So you're no longer getting it at 73, you're going to get it at 83 the first time, okay? Which is much better than getting it at 53. So you see that even with these 4 simple risk and protective factors and their profile, you can have a massive effect on whether you're going to get a disease or not. Some of it is inherent genetics, you can't do much about it, but a lot of it is also environmental, and how you behave and how you treat yourself is going to have a lot of repercussions on when you get which disease, especially these chronic diseases of late onset, all right? So look at how those 4 simple risk factors work together. And what if I told you that there are 250 plus known and proven established risk factors for coronary heart disease? Can you imagine then how incredibly complicated this picture becomes? And even the genetic risks that we know of these alleles, we know about hundreds now that can in some way contribute a tiny effect to getting a heart attack. So basically what this tells us is that no disease is ever predetermined in the way that is very clear, but every single one of us is our own experiment in space and time, and we all have our own personal risk profile which we build throughout the years of life, and whoever did whatever, this is what eventually you get. It's a combination of a phenomenal number of factors that are very difficult to grasp. So this is why it's so difficult to find some magic bullets in terms of treatments and so on, because everyone is different, even genetically, and then on top of that, everyone is different in terms of how they treat themselves and how they live. So this is why it's so difficult to find treatments that would work for everyone. This is why we're talking increasingly more and more about personalized medicine, where you try to understand each individual patient and tailor the treatments to their own risk profile. Now, to figure out if you actually understood any of that, let's pick among these 100 people on x-axis, let's pick 5 people among them, and let's answer the question, did they already get the heart attack or not? The first person is in this territory of no genetic risk, and that person is clearly here, x1, and this person smokes. So this person smokes, doesn't exercise, no high-fat diet. So would they get the heart attack already at this stage? Let's see. With smoking, they're going to lower the age of heart attack to 63, and at the moment they're 65. So clearly they had the heart attack 2 years ago, right? Because they smoked. If they didn't smoke, they would have it at 73. What about this person here? No genetic risk, smokes, eats high-fat diet, no exercise. So this person, because they're smoking, reduced the number of years needed to the heart attack to 63, then to the 53 because they also eat high-fat diet. So they didn't get a heart attack yet, they're 45, but they are very likely to get it by the age of 53. This person here exercises, no genetic risks, no smoking, no high-fat diet. Not only that this person age 60 is healthy, they are also going to remain healthy not only to 73 but to 83 years of age. They still have 23 years of full health. What about this person here? They do have some genetic risks, so because of this the heart attack should have happened here already, but they smoke also, so they should have had it here, but they exercise also, so that pushes us back. So that person probably had the heart attack at the age of 53 as well, all right? And finally, we have this person here, which is still alive somehow at the age of 75, but this person knew somehow maybe that they had the genetic risk, so they exercised and they certainly had the heart attack by this time of 53, and this was entirely because of their genetic profile. But now they're 75, so that tells us something. That tells us that even though you have bad genes and even though you're trying to help yourself, there's also a health system, and today you can get diseases but still be saved by the health system and kept alive through various interventions like heart surgery, bypass surgery, or various intervention cardiology methods. Okay, so it's not no longer a death sentence. The health system can still keep you going. So do you see how complicated picture this actually is? But this is how people eventually end up sick. Now, we are trying to understand the risk for disease as epidemiologists. We are trying to establish that some things are risks and some things are not risks. So, we could ask ourselves, how important are different risks? Can we measure somehow? Can we evaluate the importance of different genetic and environmental risk factors on human health and disease? If we want to evaluate anything, we need to measure it, obviously. So we need to measure risk. But how do we measure risk? Well, let's talk about measuring and expressing risk. Here's Jackie Stewart's Formula One. He was racing in Formula One when 1 out of 2 drivers did not survive their career. They had no seat belts, they had no safety features around the track. It was just absolutely amazing what these guys were doing. So you would think, my goodness, you're taking a career where only 1 out of 2 people gets out alive after 10 years of your career. So why would anyone want to do this? Why would anyone want to take so much risk? Well, in those days, which I was a very big fan of Formula One when I was younger, obviously, we didn't have 70 or 700 TV channels, there was usually only 1 or 2 TV channels, and on Sunday there was nothing to do ever, and 2 p.m. on Sunday every weekend there was Formula 1 race for 2 hours, and everyone in the world watched it because there was nothing else to do on Sunday 2 p.m. After lunch. So unless you were sleeping after lunch, which elderly people would, you were left alone in the house and you were watching Formula 1. This was a very exciting thing, and everyone watched it. Everyone, literally. And because of this, the rewards were obviously substantial if you're successful. As you can see here, you had all sorts of perks of this career, so some people really decided to do it. It was a bit crazy, but clearly they felt it was worth it at the time. So his absolute risk to die at some point before he retires from racing was 1 in 2 or 50%. And now we're talking about absolute risk. We are introducing the measure of risk, absolute risk. What is absolute risk? That's the probability that an adverse event will happen or not happen within some time frame. So that's what you want to know. If I have 10 years of career as a Formula 1 racer, what is the risk that I'm not going to make it? And that's what you want to find out. An absolute risk then becomes a simple probability that something would or would not happen over a certain period of time, and it's a number between 0 and 1, or a percentage between 0 and 100%, okay? And if this sounds very familiar to you, you have a time and something may or may not happen in that time, and it can be between 0 and 1. If you remember incidence, this is how we measure incidence. The only difference between incidence and absolute risk is that you can have several incident events over that period of the point in time, whereas absolute risk is usually only linked to one event. Is it going to happen or not happen? So when are you interested in your absolute risk? Well, if you're a woman aged 42 and you want to know what is the probability that your third child, which you're about to deliver, would have, or if you want to have the third child and you're already 42, what is the probability that the child would have Down syndrome? You want to know your absolute risk. You do not care if your risk is 3 times smaller than it will be when you're 50 or 4 times greater than when you were 18. That's not helpful, that's relative, but you don't need that to reach your decision. You want to know the absolute risk. So what is the absolute risk that something bad will happen if I do something? If I invest in this stock, what is the absolute risk that I'm going to lose all my money? If I sit on some roller coaster, what is the absolute risk that we're all going to fall out of it, and so on. So, and then you take calculated risks, because everything in life is a risk. It's just that some risks you're willing to take and some you are not at some point. But you could see that Formula 1 racers, even 50% risk of death in the 10 years was still acceptable to them. So they were obviously very remarkable people. Now, maternal age less than 30, we know that probability of Down syndrome per 1,000 live births is 0.7 per 1,000, 1.3 if you're 30 to 34. This lady will be in this bracket. Look at how quickly it goes up actually with age. So 13.1. So there is 1.3%, because 13 over 1,000 is 1.3%. Now this is your absolute risk. We said it's going to be between 0 and 1, or between 0% and 100%. So your absolute risk is 1.3%. Is this acceptable? To some people, yes. To some people, maybe not, all right? So some people will go for it. They want a child badly, third child. They really don't think that they think 98.7% chance of everything working well is fine. Some people will be very worried about 1.3%. They won't be able to stop thinking about it. So, everyone's different. Now, I have to warn you about something. Risks can be extremely tricky, and they can be entirely misleading, because the public perception and interpretation is that the majority of Down syndrome cases in the population will be born to mothers who are older. But truth is exactly the opposite, because of the number of births at different ages. So if you see Down syndrome cases walking around Edinburgh, it is far more likely that they were born to a mother who was young than to a mother who was old. Although these risks, you can see how quickly they go up with age, and then everyone's worried, oh, I'm old, there is a concern about Down syndrome. But look, look at the number of births. So let's say that this is some country, and 220,000 will happen in mothers less than 30, and 30 to 34, 100,000, 35 to 39, 30,000, and look how the number of births in this age of 42 drops to only 5,000. So although these are the probabilities, you multiply them by number of births, and this is what you get as the number of Down syndrome cases in the population today. So 154 of all cases that you have in your population today have been born to mothers who were actually very young. So the majority, the biggest chunk actually in all these age groups was born to the youngest mothers, and then to the mothers who were 30 to 34, because simply more births happened in those years. So when you see public perceives seeing a Down syndrome case in the street that, oh, the mother must have been old. No, in fact, she could have been 18 or 21. So it's just, this is how this is misleading. So to make sure that you really understand absolute risk as a measure of risk, I'm asking you, can it be 78% the absolute risk? Yes, it can. 0 to 100, so it can be 78%. 78% chance that something will happen. Can it be 0.03%? It's still greater than 0, and it can, and it's still less than 1. Can it be 0%? Can you think of anything that has 0% absolute risk? I think Scotland winning the World Cup in football, that's a 0% risk. Absolutely no risk whatsoever, all right? Can it be 100%? Obviously, Scotland not winning the World Cup. So it can be 100% absolute risk, okay? I mean, absolute risk of death is 100%, and maybe there's just a chance, maybe death is not like inevitable, maybe there's just maybe just highly likely. So maybe if we had 10 billion people or 20 billion people in the world, maybe there would be some people who would stop dying and just not die. Maybe death is just a very, very likely thing. Maybe nothing is 100%, Can it be 101%? No, it cannot be greater than 100%. Can it be negative 20% absolute risk? No, we don't have negative risk. It can only be between 0 and 100% that something does happen. We don't have negative events or non-events. Maybe we do in some parallel universe, but not in this one, all right? Okay, now, measuring and expressing risk, sometimes we may be more interested in comparing our risk to that of someone else rather than in our absolute risk. You remember that mother, she was not interested in comparing herself to her older self or younger self or any other woman. She was just only interested in herself and her baby and the time and what's going to happen. But what if you are interested in comparing your risks to someone else? Let's say that you've been offered 2 jobs. As a general practitioner for 115,000 pounds per year, you wish, yeah? And as a radiologist for 135,000 pounds per year. Which one will you choose? Well, you would like to make 20,000 pounds more a year, but you don't want to get cancer because of your work, and there may be some risk if you're a radiologist that you would. So you want to know how your absolute risk of cancer by the age of 70, say, compares to that of general practitioners. If you have 2 times greater risk than a general practitioner to get cancer, but you make 20,000 pounds more every year, maybe then that's going to sound like an acceptable thing. But if you have 5 times greater risk than a GP, is that then acceptable for 20,000 pounds a year? Well, everyone's different, I don't know, but maybe. So, relative risk is something that you can measure by dividing absolute risk of one group with absolute risk of another group, and then you get some number. This number tells you how many times is the risk of one group greater than the risk of other group, okay? How many times? Relative risk is the number of times that an exposed person is likely to become diseased relative to a non-exposed person. And basically, it is you get it by dividing 2 absolute risks with each other. So it's incidence in exposed versus incidence in non-exposed, but in fact, it's an absolute risk of exposed over the absolute risk of non-exposed. So in this case, absolute risk is the same as incidence, all right? Now, let's go back to our Down syndrome example and think of relative risk. So you remember these maternal ages and probability of Down syndrome, this was absolute risk. Now let's think of the relative risk. Let's say that ladies in younger than 30 have this probability of Down syndrome, which means that relative risk of one lady in this group versus another lady in this group is the same. If it's the same, then I mean the absolute risk is the same, so you divide two same things and you get 1. So relative risk of any woman less than 30 against any other woman less than 30 would be 1. But let's say that now you have ladies who are older, and they are now wanting to know their relative risk in comparison to this youngest age group, and look at how many times more likely they are becoming to have a child with a Down syndrome. 1.9 times, 5.3 times, 18.7 times, and 49.4 times. So 50 times more likely to have a Down syndrome child aged 45 or more than in less than 30 years age groups. 50 times more likely. So if you told a lady that she's 50 times more likely to have a Down syndrome child than when she was less than 30, she would be too scared to have a child. But in fact, the probability is 34 per 1,000. Remember? So it's only 3.46%. So can you imagine now, and can you understand how can media get click bites and make things sound spectacular? What do you think media will say? Media will say, ladies over 45, 50 times more likely than ladies under 30 to have a Down syndrome child. They're not going to say ladies over 45 only 3.46% chance to have a child with Down syndrome. That would not sell any newspaper, but 50 times more likely, that gets everyone's attention, right? Okay, let's see if you understand the relative risk as a measure of risk. Do you think it can be 78%, the relative risk? So what are we dividing? We're dividing one number between 0 and 1 with another number between 0 and 1. So it can be anything which you can get by dividing one number between 0 and 1 with another. So 78% is a strange thing for relative risk, isn't it? Because that's number less than 1. You want to have relative risk of 2, 3, 5, 7, because if it's a risk, then it should make you more likely. 78% means that you're actually less likely than 1. This means that this is a protective factor if the relative risk is 0.78. That's less than 1. That means that something is protecting you from the disease. It can be 2, it can be 200, it can be 0.5 in the same way, it can be 78%. Can be 1 in 700, that's odd because it's such a tiny number and we're measuring some risk. So this is something phenomenally protective rather than risky. Can it be 1 million? Can a relative risk be so big that someone is 1 million times more likely than someone else to get some disease over some period of time? Well, it actually can, because if you have two towns in Africa, both with million people, and malaria is a big problem in one and not in another one, and you just have one person from other town who traveled to the first town and contracted malaria, so the incidence in the second city really is 1 in a million in a year, whereas the incidence in the first city, maybe everyone got malaria in that year and it's 1 million. So obviously this is very exaggerated and it's not realistic, but I can think of the cases which are analogous, where you can say that some countries have 1 million times greater risk than other countries of some health event, all right? So, let's say there's some epidemics that affects a million people in some very large country and just one person who traveled to that country in another country, then it could be a million. Can it be negative too? Can relative risks be negative? Can you divide a number between 0 and 1, which is a positive, with another number between 0 and 1, which is again positive, and get a negative number? No, I don't think you can. Can it be 0? Can a relative risk be 0? Obviously, the numerator need to be 0, and absolute risk would need to be 0. So I guess it could be 0. The relative risk could be 0 if the numerator, if the absolute risk of those exposed to risk are 0. Which is again a very strange case, but theoretically possible. So it can be anything that you can get by dividing a number between 0 and 1 with another number between 0 and 1. So we learned about absolute risk, we learned about relative risk, which we can calculate only by having absolute risks, as known. But many times you want to blame something on someone, and you want to know which part of the damage is attributable to some risk that preceded the damage. So what is this now? Let's say there was a Chernobyl incident, and we had cancer rates in the USA and Belarus comparable in 1970s and early 80s, and then the Chernobyl accident happened. So all of a sudden, we were no longer interested in relative risks between Belarus and America, or absolute risk in America or Belarus. We were interested in what part of the incidence of cancer after the incident could have potentially been attributed to this incident, and what part was just expected. And look at this graph. So this is 1969 and this is 1986, 7, 8, 9, 1990, and so on and so on and so on. So we had, this is incidence per 100,000 people in Belarus. This is the cancer incidence, number of cases per 100,000 in children, young adults, and adolescents. Look at this. So basically, in children, it was 0.1, 0.3, 0.2, and then the incidence happened. And look how this went up to 4. 4, which is 20 times more than what it was here. So 20 times more. So that means 19 out of 20 cases were really happening at that time in children due to this incident. And then children became adolescents and young adults, and the new children were being born who were not exposed, so the rates went down in children. But in adolescents and young adults who kept being followed, and look at what was happening. My goodness, adolescents who also, they all had 0.2. Adolescent, it went to 11.3. This is 60 times more cancer. And if it's 60 times, 59 out of 60 cases were attributable to this incident. Only one that wasn't. And then young adults here, again, 35 times more cancer. 34 out of 35 cases were entirely due to this incident, because nothing else can possibly explain this enormous hike in cancer rates. So now we're talking about attributable risk, which is measuring excess risk, which is due to a particular risk factor, like increase of cancer incidence after this accident. How do we define attributable risk? Well, this is the additional or excess risk of exposed people to disease compared with persons who have not been exposed. So you're attributing the risk to this exposure. And you can easily calculate attributable risk by subtracting the absolute risk in the non-exposed from the absolute risk in the exposed. And this is exactly what I was doing in my head while I was showing you this graph. So the absolute risk of exposed was, say, 4 per 100,000. Absolutely risk in non-exposed was 0.2 in 100,000. And you subtract this and you get big difference. And then the properties of attributable risk as a measure of risk, you can ask yourself the same questions as I did for relative risk, and then you're going to see some strange things. Because here it can be anything that you can get by subtracting a number between 0 and 1 from another number between 0 and 1, suddenly this can actually be negative. All right? So remember, attributable risk can be negative. A combination of relative and attributable risk is very useful, because sometimes relative risk doesn't tell you a full story. It looks really big, but the attributable risk is small. And then sometimes attributable risk looks big and the relative risk is small. So it's really good to know both. And media, again, is always going to pick up the most spectacular one, and you don't trust it until you also think what is the attributable risk. For example, the attributable risk of car accidents leading to serious injury caused by young and inexperienced drivers in their first year of driving is 10% in both UK and Bolivia. How come? In the UK, absolute risk for experienced drivers is 2 per 100, for inexperienced 12 per 100. This means that attributable risk is 10% and relative risk is 6. So in the UK, young drivers are 6 times more likely to have to cause a serious injury than the experienced older drivers. 6 times more. That's a lot, and that's a real thing. But what's happening in Bolivia? Absolute risk for experience is 20 in 100, for inexperienced 30 in 100. So attributable risk again 10%. It looks like it's the same thing, the same situation, but relative risk only 1.5. How come that inexperienced drivers have only 1.5 times more risk than experienced drivers? And we can ask ourselves, how come that experienced drivers have such a high risk, absolute risk of accidents in Bolivia in comparison to UK, 2% and 20%, so 10 times more risk. What is it about Bolivia to cause so much accidents even in experienced drivers? Well, if you've been there, you would know, because this is what the roads look like in Bolivia. You don't really want to take them unless you really are sure that there haven't been any rains recently, and you know, this doesn't really look very safe for anyone, does it? So then we get to the question about what is population attributable risk. Well, population attributable risk is a very useful concept. Let us consider an example. Sometimes you're a chief of health system in your country and you need to decide what proportion of disease burden could you remove by completely removing the exposure to a well-documented risk factor. This number will also tell you what proportion of disease burden in the population, like myocardial infarction, is directly attributable to the specific risk factors such as smoking. So, for example, if you know that smoking can cause myocardial infarction, but you know that it's only one of the more than 200 or 300 established risk factors for myocardial infarction, you're interested in what specific contribution to the overall burden of myocardial infarction in the population you can attribute to smoking. You can only know this by removing smoking from the population and then see what happens to the burden of disease. To compute this proportion, we need to know the proportion of population which is exposed to this risk and the effect size of that risk, which is, as we know, measured as relative risk in the exposed in comparison to those who are not exposed. So let's think of this myocardial infarction example. Let's say that you have a population here, and this is the burden of myocardial infarction which you can expect to happen in this population, all right? And now, high-fat diet, 20% of population exposed, and this is its contribution in addition to some baseline risk. Smoking, 20% of population exposed, and this is the contribution of smoking. And it's bigger than the high-fat diet. Why is it bigger if in both cases only 20% of population is exposed? Shouldn't it be the same additional burden? Well, this is where the relative risk kicks in. Clearly, smoking has a higher relative risk, stronger effect size than high-fat diet, which means that 40% of population would need to be exposed to high-fat diet to have the same effect on the burden of myocardial infarction as does 20% of people smoking. Or even worse, if 40% of people smoke, they would have far bigger effect on the burden. And then some people exercise, and thanks to that, some of the burden is removed, all right? So now when you know this, definition of population attributable risk is really the incidence of the disease in the population, which is attributable to exposure to the particular risk factor, and you take away that risk factor and you lose that part of the incidence, that portion of the incidence. This is how you calculate it, and in comparison to smoking and in example of smoking and myocardial infarction, this is what the numbers would be. You know, you would be subtracting 1 from relative risk, and this is the proportion of exposed, and this is basically how you work it out. And if you removed smoking from from the population entirely, you would reduce the incidence of myocardial infarction by 28.6%. This is what would happen. So this is the only way you can really know how an individual risk factor contributes to the incidence or the burden of disease, by removing it and seeing what happens. Because you can speculate that smoking causes 80% of lung cancer or 70 or 60, but you don't know how many other factors also play a role. You can only know how important smoking is when you completely remove it from the population, and then your lung cancer is reduced by 50, 60, 70%. You see exactly what it is, all right? Okay, so back to that architecture, we can think, what are the properties of population attributable risk? Can it be 78%? Can you remove 78% of the burden? Yes. Can it be 0? Yes. Can it be 100%? Can some risk factor by removal remove all the burden? I guess yes, but it can't be 120%. Well, now if relative risk is less than 1, so if it's a protective factor, then the population attributable risk can actually mathematically be negative. But remember, in that case, that is a protective factor. So this means that by exposure to protective factor, you're removing the burden, basically. So can it be 5, negative 100, negative 150? Think for yourself. Think carefully. It can be responsible for 0 to 100% of the removal of the problem if it causes harm. But it could also remove 0 to 100% of the problem if it helps, and in that case it's negative. So vaccine would have a negative population attributable fraction because it would be removing the problem. So if it's helping and it's negative or protective, it's called potential impact fraction. So no longer population attributable risk, but rather potential impact fraction. So that is the proportion of the burden which could be removed through helpful intervention. Now, if you want to use cohort study to assess risk of disease, you can do this. So as you remember, you start with exposed, you start with non-exposed, you follow them up for a number of times, years or months or whatever, and you see different incidents for different groups. So you can easily calculate absolute risk of smokers here to be 60% after this period of time, non-smokers 20%. Attributable risk of smoking is obviously 40% because you subtract them. Relative risk of smoking clearly is 3 because you divide them. And most interesting is always this relative risk or effect size. We're trying to prove that it's greater than 1. But if you're using case control study to assess risk of disease, this is how you do it. You look at the odds of exposure. You can't have absolute risks anymore. You can't have attributable risk, therefore. You can't have relative risk, therefore, because you don't have absolute risks to calculate them from. So don't ever say that in a retrospective study you can have relative risk or attributable risk, because you can't. You can't even have absolute risk. All you can have is an estimate of relative risk, which is called odds ratio, and that is the odds that a case was exposed divided by the odds that a healthy control was exposed. And this is how you calculate it. If this is A, C, B, and D, then this is how you calculate it. You get 3.5, and that's actually quite close to what we believe relative risk for smoking to be in relationship to myocardial infarction in this case then. So let's compare these two studies. What are advantages and disadvantages of prospective and retrospective study? Prospective study or longitudinal or cohort study is always better than retrospective because it's less biased. It allows us to directly measure absolute risk, attributable risk, and relative risk. It's excellent for evaluating the effect of one risk on several diseases because you start with one exposure and controls, non-exposed, and not controls, non-exposed. And you start with them and basically you follow, and you can follow the effect of this risk factor on all sorts of diseases. But if you want to study many risk factors, it's obviously not good because you always have to start with a group of exposed. So in a retrospective or case control study, these studies are prone to bias much more because the disease status is already known, and you cannot measure absolute, attributable, or relative risk. You can only estimate the relative risk as odds ratio. But they're much cheaper, much more quick, much easier to conduct. They're excellent for evaluating several exposures as risks for a single disease. You start with the disease and controls, and you can ask them for all sorts of exposures. And they're much better for studying rare diseases than common diseases. Why is this? This is going to be your homework. Think about it, all right? Thanks very much indeed.